3.6, a summary of curve sketching. Okay, so here we're going to use the information from a graph, a given graph, and we're going to use it to answer questions about the graphs of functions that are not given. So the graph of the derivative of a function f on the interval -4 to 4 is shown. So this is the derivative. Answer the following questions about f, justifying each answer with information obtained from the graph of f prime. It should be. Okay, so this is f prime. This is my derivative. My job is going to be to answer questions about the original function's graph, simply just f, by looking at the derivative. Okay, so A, on what intervals is f increasing? Well, f is going to be increasing whenever f prime is greater than 0. So you look at this graph and you try to figure out where is this graph greater than 0. And greater than 0 means positive. So this graph is positive or above the x-axis from -4. And you know what? Let me change to a highlighter. From -4 all the way up to right there. It is above the x-axis, therefore it is positive. And then it is negative from here to here. So where should my original function f be increasing? It should be increasing wherever f prime is above the x-axis. So that is from -4 to 1. Now, proper justification or explanation would be f is increasing wherever f prime of x is greater than 0. And f prime of x is greater than 0 from -4 to 1, so that is where f is increasing. Okay, I'm just going to shorten it, right? Since f prime of x is greater than 0. Now, notice our critical numbers. For example, -2 probably would have come out to be a critical number that you would have had to check, but then once checking you would have seen that it was not a min or a max. Because the sign doesn't change, f prime is still positive. And then we call this a shelf point, by the way. It's usually just a point where there's a point of inflection. The concavity changes usually, but it's not a min or a max. A good example would be x cubed, right? A cubic. Right about in the middle here, that is the point of inflection. Okay, let's see, what else? D, on what interval is the graph of f concave up? Oh, you know what? Before I go on, here's the other critical value right there. Yeah, okay. On what intervals is the graph of f concave up? Okay, so concave up means, right, happy face. Now, it's kind of hard to tell where it's a happy face when I don't have f. This is not f, this is f prime. But, if you recall, I've said the first derivative, if I were to derive that, I get the second derivative. So the second derivative is the first derivative of the first derivative. If I can use the first derivative to tell me stuff about the original function, then I should be able to use the second derivative to tell me stuff about the first derivative, because it is the first derivative of the first derivative. And vice versa, I can use the first derivative to tell me stuff about the second derivative. So, in order to tell concavity, you need the second derivative. I don't have the second derivative, but I can use what I know about this first derivative to tell me stuff about the second derivative. And then when I get that information, I can use that to answer for f. Okay, let me change pens. Let's do blue. Okay, so on what intervals is the graph of f concave up? Well, let's look at f prime and figure out where is it increasing and where is it decreasing. So, wait, okay. So from -4 to -2, it is decreasing. I'm gonna delete this arrow. Um, and I'm gonna guess this one. It's gonna be an estimate. I know that it's off to the side, but I'm gonna treat it as 0. Okay, just to make our lives easier. From -2 to 0, it is increasing. And then from 0 all the way to 3, it is increasing, or decreasing, sorry. And then from 3 to 4, it is increasing. Okay, so this increasing and decreasing is telling me stuff about the second derivative. These are the slopes of the first derivative, which tells me what's happening with the second derivative. So wherever it's a minus, that's concave down, and whenever it's a plus, it's concave up. And that is the information I need for the original f. Okay, so let me recap. I have the first derivative. I am using its increasing and decreasing to tell me what f double prime is doing. Alright, so as far as concave up goes, wherever the pluses are, that's where my function is concave up. And obviously, the negatives would be concave down, but since they didn't really ask for that, I'm just going to answer concave up. So concave up is going to be from -2 to 0. And I am using that 0 freely, because it really looks like it's a little off to the left there, but whatever. My notes. So -2 to 0, and from 3 to 4. So concavity appears to be positive there. And that is because f prime, because remember this is the graph we have, is greater than 0. It is positive. It is increasing there, right? Or, I'm sorry, not greater than 0, just increasing. I don't know why. Brain fart is increasing. So because these are the intervals where this graph is increasing, then f double prime is positive. Okay, and positive means concave up. C, at which x coordinates does f have a local extrema? Okay, so earlier I mentioned that this right here, x equals 1, is a critical value, right? Because my slope is equal to 0. So it appears to have a min or max at x equals 1. If you want to figure out if it is a min or a max, all you got to do is go back to the stuff I highlighted. The green and the pink, right? Or purple, whatever color you want to call that. The green is telling me that it is positive. So the original function is going to be increasing, increasing, increasing up to 1. So something like this. And then decreasing, decreasing all the way to 4. So something like that, right? So this is a maximum. So we have a maximum at x equals 1. Now, closed intervals are a little bit tricky because if my original appears to look like my little sketch here, then that means that my endpoints could possibly be mins and maxes, right? So my endpoint is -4 and 4. Now, if this is what the graph somewhat looks like, if it was strictly increasing and then it's changed to decreasing, then that means that my two endpoints could possibly be mins, right? I'm going off of my sketch from the information. So it's very much possible that I could have a minimum, or minimums, minimi, I don't know if you say that plural, at x equals -4 and positive 4 because my endpoints could be mins and maxes, right? And judging by the behavior of what the function is doing, right, going up and then coming down, it is very much possible that at negative 4 and 4 I have two minimi. I don't know, that's how you say that plural. Okay, D. What are the x-coordinates of all the inflection points of the graph of f? So remember, inflection points are when concavity changes. If you recall, these up here are what told me concavity. So where does concavity change? So at x equals negative 2, so right here, it goes from negative to positive. And then the next one is positive to negative, so it changed again. So at this x, so let's see, I have x equals 2, I have x, or sorry, negative 2, I have x equals 0, and then it goes from negative to positive again. So right here, at x equals 3. So those are my points of inflection. So x equals negative 2, 0, and 3. It's a negative. Okay. E. Sketch a possible graph of f on the interval from negative 4 to 4. So now I'm possibly sketching a possible graph. Now, my little ghetto sketch here didn't take into account concavity, right? So it's not really that great. It's okay. It's not really great. So what I like to do is, and I put it close enough on your paper that you can do it too. I'm going to erase this. Get it out of my way. Okay. I'm going to move this up. So really what I like doing is, you know what, I'm going to erase this just to have less junk. Alright, my rough sketch. If you recall, critical values, right? X equals 1 is my critical value. I decided was a maximum, right? So I'm just going to, just anywhere, up high. There you go. Now, remember, the negative 4 and the 4 are my minimums. So let's make one down here. And let's make one right there. Why not? Minimums. Okay. My rough sketches. That's horrible. But anyway. Using the highlighted part. The green says increasing. So this has to go up. And then the purple or pink or fuchsia, whatever you want to call that, down. Oops. I didn't finish that line. Come on now, baby. Fix yourself. Okay, so let me do that again. Alright. Now, roughly this is what the sketch looks like. Only curvier. But the curves that I want to figure out, I'm going to figure out by using the concavity. So if you look here, right, you can see that. That's my concavity. So up to negative 2, this function is concave down. Remember, concave down is like unhappy face. So I'm just going to add a little curve to this. Okay, concave down to negative 2. And then I'm going to do red for concave up so you can see the difference. From negative 2 to 0, it's happy face. Concave up from negative 2 to 0. Now, I still have to be strictly increasing, right? Because from negative 4 to 0, or sorry, from negative 4 to 1, I should be increasing. So I'm doing my very hardest to not make this look like it's ever decreasing. Alright, what's next? From 0 to all the way to 3, we're unhappy face again. So from 0 all the way to 3, we are unhappy face. Right? So there's my maximum still, right here. I'm off by a little. Forgive me, right? And then from 3 to 4, we're concave up, so that's happy face. So we're like this. Okay, so I know it looks horrible. It looks like some kind of Christmas something. Christmas worm. But basically, what's happening here is I'm trying to adhere to the fact that yes, there are places where this function is concave up and concave down, But I also needed to pay attention to the fact that this function is strictly increasing all the way to 1, but then from 1 and on to 4, it is decreasing, and I kept that. I stayed true to that. So basically, still bad. Let's try this again. Alright, close enough. So I'm just gonna steal this right there, and I'm just gonna make all of my sketching disappear, and then I'm gonna break this down a little. Not that it matters. That's roughly a sketch of F. Okay? So this was F, remember? And this was F prime. Alright. Example 2. The graph of the position function y equals s of t of a particle moving along a line is given. At approximately what time is the particle's velocity equal to 0 and acceleration equal to 0? Okay, so this is made way easier just by translating some of these words. Oops, that's not what I meant to do. I meant to move it. So, velocity. What is it? And I'm hoping you're saying to yourself, first derivative, right? Slope, first derivative. So basically, they are asking when is the first derivative equal to 0? If this is my original function, my first derivative should equal 0 whenever I have a maximum or a minimum. Another maximum. Okay. So, that's awful. Okay. So, let's see. 1. This is about, oh, yeah, that's right. I'm going to call this 2. Okay? I'm not trying to make my life harder. On the paper, it probably looks better. It doesn't help that I made my dot off to the side there. So that's 2. Okay, this is 6, no problem. You know what? Let me do the dotted line. This looks like the peak to me. I don't know. Let's just make our lives easier and call that 9.5. 9.6, 9.7, whatever. But humor me, people. Okay, so answer for A. Velocity is equal to 0 at these 3 points. X equals 2, 6, and 10. Alright, answer for B. Translate. Acceleration equal to 0. Acceleration is what? Okay, so obviously, I'm hoping that you're using my translation for velocity the same way, right, that I said velocity is the first derivative. I hope that in your brain you're saying, oh, acceleration is the second derivative. I got lazy and I wrote second. So when is the second derivative equal to 0? Oy, so when is the second derivative equal to 0? So if you think about it, the second derivative test, we find the zeros, and then it tells us where the original function, or the original function's graph, is concave up and concave down. So, second derivative being equal to 0 is basically how you would find the points of inflection, the poi. But see, we have the original function, so I can tell you where it's concave up and where it's concave down. So here it is concave up, here it is concave up, right? And then this is, or I'm sorry, I'm saying that backwards, concave down, and here is concave up, and then just the end is concave up. Now, the acceleration equaling to 0, basically, the second derivative being equal to 0 is the places where you will find the points of inflection. So, where does it appear to be that the concavity changes from up to down or down to up? Now, again, I'm estimating here. I'm not going to make my life harder. I'm going to estimate that about right there is where it changed from being concave down to concave up. So we're going to call that 4, right? If you need me to make this a little longer, I can do that. And then moving on, where does it appear again that the concavity changes from up to down? And if I had to guess, I would say that it's about right there. 8 looks good. I don't think they would ever make you forcefully guess. I think they would be a little more uh, helpful in figuring out where these locations are, okay? In case you're wondering, oh my god, how am I supposed to do this on the AP exam? And then the following one, if I had to really guess, eh, I don't know. It's a really close call between 11 and 12. Let me erase all of my stuff. This seems to be concave up, concave up, concave up. I don't know, 11 or 12. Let's call it 11. Okay, so there you go. This was made easier 100 times, I hope, by simply changing this word to first derivative and this word to second derivative and figuring out, okay, what does the first derivative test? When I equal it to 0, what does it give me? It gives you the critical values, the max and the mins, right? What does the second derivative test give me when I set second derivative equal to 0? Oh, well, that's the places where I can tell the concavity changed. All right, example 3. Sketch a smooth curve. Y equals f of x through the origin with the properties that f prime of x is less than 0 for x is less than 0, and f prime of x is greater than 0 for x is greater than 0. Okay, this is really easy. X is less than 0 from here to here. X is greater than 0 from here to here. This is saying that the slope is less than 0, so negative. If my slope is negative, I am coming down. Now, this over here is saying, oh, that's not what I meant to circle. This right here is saying that my slope is greater than 0. If my slope is greater than 0, then I'm going up. You know what? I should have color-coded this. Let me make this one blue, because that's the blue section. And let me make this red, because that's the red stuff. Okay. So, what does my graph look like? Well, for the red part, it's coming down. For the blue part, it's going up. And voila, there is a very rough sketch. Oh, you know what? I forgot to stress this. Through the origin. Remember, back algebra 1, origin means 0, 0. That means it has to go through 0, 0. Okay? But anyway, basically some funky looking parabola. Example 4. A continuous function f has a domain of 1 to 25 and range of 3 to 30. If f prime of x is less than 0 for all x between 1 and 25, what is f of 25? Okay, so this is a lot easier than you think. If you recall, domain is the x's, where the range is the y's. So basically, if I were to make some little rough sketch, they're saying that for this function, all the x's that exist are from 1 all the way to 25. And all the y's that exist are from 3 all the way to 30. And then they give us this piece of information that says that f prime is less than 0. My slope is less than 0, which means my slope is negative. If my slope is negative, then that means that my continuous function is strictly decreasing. Right? It's going down like this. I mean, it could be a funky curve, but it's just going down. Be a straight line, whatever. It's just a continuous function that's just going down. All right. if it's just completely going down and the lowest x is 1, but the highest y is 30, then it would make sense that it would start up here and then work its way down to 3 until it gets to 25. Because if it is strictly decreasing, there is no way that it would be doing something like, I don't know, like dee 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 dee. It can't do that because now it went up and then came down, right? So that's out of the question. Um, you can't say that, well, what if it started here and then it went down? Well, then 30 and any number that you left out is actually not part of the range. Okay? So, critical thinking, right? Common sense, logical thinking, whatever you want to call this. Basically, our function looks like this. Okay? It is strictly decreasing. So 30 is the highest y value, so that must mean that that's the highest point. And 3 is the lowest y value, so 3 is the lowest point. But for x, since it just keeps going down, 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 1 has to be the highest and 25 has to be the lowest, where the lowest point is located. So what is f of 25? So f of 25 should be the lowest point. Right. Last one. True or false? Oh no, second to last one. A continuous function on a closed interval must attain a maximum value on that interval. Justify your answer. Okay, so a continuous function on a closed interval. So if I have a continuous function, anything that is continuous on a closed interval, right? Um, it's saying that it must attain a maximum value on that interval. Justify your answer. True. If it's continuous, it keeps going, right? It's a closed interval, so either the endpoints are a maximum, or somewhere in the middle there's a maximum, right? Oh, this one's not very well drawn. Okay, so like for this example, that would be the maximum. For this example here, that would be the maximum. For this example, this looks like the maximum. For this example here, I didn't draw this that good either. But let's say this is probably the highest point. Okay? There has to be a maximum point if it's a closed interval and it's continuous. Actually, this is guaranteed to us by the extreme value theorem. So that's my justification. Okay, this is true. This is guaranteed by the extreme value theorem. Guaranteed by the extreme value theorem. And you can reread that if need to. Alright, example 6. True or false? If f prime of c equals 0 and f double prime of c equals 0, then f of c is a local maximum. Justify your answer. Alright, f of c. So let's say we were doing the first derivative test, right? And so we have the first derivative test. This is c. First derivative test is supposed to tell us, oh, okay, plus or minus, right? But if we also have the second derivative test, and c is where it also equals 0, then that means that my inflection, or my concavity, changes here. So it went from being concave up to being concave down. Well, how could this C possibly be a maximum if it's where it's changing from being concave whatever to concave whatever? See, yes, this would be a maximum, right? For my little made-up sign chart here. But C cannot also be the location of a point of inflection. It cannot. Okay, you cannot have a point of inflection in the same place that there is a maximum. This is false. An example would be a cubic. Oops, I don't know what I did there. A cubic. Okay, let's erase that. Use a cubic. The cubic, concave up, or down. I keep saying that wrong. What's wrong with me? Concave up. See right here? This is where my concavity changed. That would be my C value in this scenario, basically, or in a reverse scenario of that. If that is my point of inflection, there is no way that that is also a maximum. Okay? You can't have a maximum whenever you have a point of inflection. Alright, we're done.